All right, welcome to Chapter 7, Section 1, Laplace Transforms. All right, at the end of this online lecture, a student should be able to uh, understand the definition of a Laplace transform, how to find a Laplace transform using the definition, how to find a Laplace transform using the table of Laplace transforms, how to find an inverse Laplace transform using uh, the table of Laplace transforms, the definition of a unit step function, and how to find the Laplace transformation of the unit step function. All right, so what is a Laplace transform? So you have done this mathematical operation called a derivative that transforms the function into the derivative of the function. So the idea of a Laplace transform is the same type of thing. We're going to operate on a function that's in the time space and transform it into Laplace space. Why do we do this? Well, we have these differential equations, and the Laplace transform does an operator and takes this differential equation and transforms it into an algebraic equation. So hopefully it's easier to solve. All right, so what is the definition of a Laplace transform? It's the integral from 0 to infinity of our function that we want to transform times e to the minus st dt. And as we integrate this, it should converge to a particular value. So let's apply the definition. Let's say I want to take the Laplace transform of 1, which is a constant. So I plug that into my definition, and I have to do this integral. So what is this integral? We've done it many times before. I do a u substitution of s and t, and then my du becomes s dt. I make my substitutions, and I have to do this integral, and I can factor out the s's because I'm only integrating over u, not s. And then I can do my integral, which would be this. And then we evaluate our function at our limits of minus infinity to infinity, sorry, 0 to infinity, and I get this. Well, evaluating the exponential function at minus infinity gives us 0. Evaluating at the exponential function at 0 gives us 1. So we get a minus 1 from doing the evaluation, and we get a Laplace transform of 1, a constant, is equal to 1 over s. All right, so let's try another one. Let's do the Laplace transform of e to the at. That's a function we run into a lot in our differential equations. I have to plug it into my definition and do some algebra, and I have to do this integral. Well, this is very similar to what we've done before. What I'm going to do is apply this substitution, and this can make my du equal to this. So I plug it in, I have this substitution, integrating over u, not s or a, so I can factor that out front as a constant, and then I do my integral that we have already done, evaluating at its limits, and I get the integral, the Laplace transform of e to the at is equal to the Laplace transform, is equal to 1 over s minus a. So let's try another Laplace transform. Let's try the Laplace transform of cosine of at. Again, I have to apply my definition. Now this integral is a little trickier. I'm going to try a substitution of u, but I have to use a different integration method this time. I want to use integration by parts, and so I have to use the integral of u dv is equal to uv minus the integral of v du. So I need to find my u's. I'm going to find u is cosine at. That gives me my du of this. I'm going to define my v, or I should say my dv, as e to the minus s of t dt, and that gives me a v of this. We plug that back into our integral, and we get this value. So I definitely have my u's. There's my u, and there's my v, and then here's my v, and my du is in here, here, and here. All right, so I need to evaluate this. Let's do some algebra and evaluate its limits again. That's 0 because the e to the minus infinity is 0. This is going to be 1 over s because e to the 0 is 1 and cosine of 0 is 1. And so what's going to happen is I'm left with this integral. Well, I have to do the sine integral. So we're going to do integration by parts again. It's very similar to what we had before. I plug everything in. All right, so we start with evaluating our limits of the first term. And we find out that that term goes to 0 because e to the minus x goes to 0. This term goes to 0 because sine of 0 is 0. And what we come up with is that we originally started out with the definition of the Laplace transform of cosine of a of t, and we find out that that is equal to this expression, the 1 over s minus a squared divided by s squared times the same integral. So if we do some algebra and move them around, I can factor out our integral, and we can find an answer for the integral to be this. And that would be the Laplace transform of cosine of at. Now, that doesn't look like anything in one of the tables, so I'm going to have to do a little bit of math here. So let's multiply through by the s, and we get that. And then I'm going to multiply by a factor of 1 of s over s. And if I do that, I get this term. And so what happens is the Laplace transform of cosine of a of t is equal to s divided by s squared plus a squared. All right, so that's how you find the Laplace transform of cosine of a of t. Now, Laplace transforms have some properties. They have distributive properties and commutative properties, just like a lot of other algebraic ideas. So what we can do here is if we have a constant times a function and the sum of two functions, what we can do is distribute the Laplace transform to each individual function and also factor out any constants. So we're going to use those properties to do more complicated Laplace transforms. So you can also have inverse Laplace transforms. So once we have the Laplace transforms we solve for our solution, we want to get back into the time domain because we've solved everything in the Laplace domain. You remember that we found the Laplace transform of e to the ax. And then the idea is you'd have to find the inverse Laplace transform of 1 over s minus a. Now to do that, I know that 1 over s minus a is the Laplace transform of e to the ax. And so if I have the Laplace transform of a function and I take the inverse Laplace transform of that, I just get the function back itself. So that's the technique that we're going to want to do. Same way with Laplace transforms for 1. I know I want to take the inverse Laplace transform of 1 over s, and I know 1 over s is Laplace transform of 1, so the inverse Laplace transform would be just equal to 1. So let's try it with one more time with our cosine of at. And again, I know that s divided by s squared plus a squared is the Laplace transform of the cosine of at. So that this should be the inverse Laplace transform of that should be cosine of AT. Now, this is great if you want to do a lot of integrals, but these integrals have been done before, and they're in this integral table, just like this. So if you want to take a Laplace transform, you can look it up in this Laplace transform table. Now, this table has a few things that we haven't dealt with before. So there's this gamma function right here, and the definition of the gamma function of a plus 1 is equal to a factorial. So we need to know that. And then there are much larger Laplace transform tables in the inside cover of your textbook, and these tables will be given to you for exams, so you don't have to memorize the Laplace transforms. Although if you use them enough, they will get stuck in your long-term memory. All right, so it's the same way with inverse Laplace transforms. Instead of going from the first column to the second column for Laplace transforms, you have to go from the second column to the first column. So what we have to do is, let's say we have this function of 1 over s cubed, and I want to take the Laplace transform of that. So I look in this Laplace transform table for something like that, and the closest one I have is this one right here. So what I'm going to do is, that's the closest one I have, and so my n plus 1 has to be 3, so that means my n has to be 2, but I don't have a 2 factorial. Well, 2 factorial is just 2. I need to get a 1 up there, so what I have to do is, if I multiply 1/2, if I multiply by a factor of 1, and that factor 1 is 2 over 2, then I get a constant here times the function I'm trying to take a Laplace transform of. And this turns into this. So if I take the Laplace transform of this function, I should get the Laplace transform I want. So that's what I'm going to do. Now, using the property of Laplace transforms or inverse Laplace transforms, I can factor out a 1/2, and now I have a Laplace transform that shows up in the table, and that is equal to t squared. So over here says, right here, that that is equal to t to the n, and our n is 2. So the inverse Laplace transform of 1 over s cubed is 1/2 t squared. Let's try this out on another function. What is the inverse Laplace transform of s plus 2? So I look over here, do I have any s plus 2's? I don't see one. I do see this one right here. That's close, so let's see if I can rewrite it. I'm going to rewrite it as s minus a minus a. And if I do that, I get my plus. And in this case, Ra is a minus 2. So applying the inverse Laplace transform of this, I will get e to the minus 2t, because my a is a minus 2, and I plug it into there, I get e to the minus 2t. All right, let's try another example. Let's find the Laplace transform of 2 divided by s squared plus 9. And if you look over here on the table, the closest one we have of that is the sine one right here. It's not the cosine one because I don't have an s on the top. All right, so let's see what we can do. In this case, to get the right k, I have to have a 3. But see, mine has 2 here. It's not a 3. So what I'm going to do is multiply by a factor of 2/3. And that should give me my expression I have over here. So these two things are equivalent. They're just written in a different mathematical representation, so I can apply my Laplace transforms or inverse Laplace transform. So I can factor out the 2/3 and then use the sign, and then so it should be 2/3 sine of 3t. Okay, well, my slides are in a little bit of different order, and I apologize for that. I'm just in a bit of a hurry today. Okay, so definition of a unit step function. So what is a unit step function? Well, that's the definition right there, and the idea is it is 0 when t is less than 0, but it's 1 when t is greater than 0. So there's our graph of our unit step function. So it's kind of like a switch. It is 0 until we hit the t equals 0 line, and it gets switched on to 1. Now it can be represented in two ways. This is one way. The other way is this way. This is what I call a shifted unit step function. It is 0 up to the point A, and then it turns on and goes to 1 at A. So the first one turns on at 0 because if you look at them, A is 0. And the second one turns on at any value of A. So that's what the unit step function is. So we need to find the Laplace transforms of a unit step function. So we're going to apply the definition. Now if we do that, I'm going to break it up. I have to do this integral. And what basically my function is equal to 1 after 0, and that's when I do my integrals from 0 to infinity. And so all I have to do is integrate that function, which we've done before. It's 1 over s. So here is the shifted unit step function, and I apply this definition. Now this is a little different. My function's not 1 until I hit A, so what I'm going to do is break the integral up into two parts. I'm going to break it up, integrate it from 0 to A, and then integrate it from A to infinity. And if I do that, that integral is 0 because the unit step function is always 0 up until A. And then all I have to do, and then the unit step function goes to 1 between A and infinity, and so I just have to do this integral again. And we've done this before. So we make our substitutions and solve the integral and evaluate our limits. And of course, e to the minus infinity is 0. And so what we get out of it is the Laplace transform of the shifted unit step function is e to the minus at divided by s. All right, so Theorem 2, the existence of a Laplace transform. So a Laplace transforms will exist if the function is piecewise continuous for t's that are greater than 0. Basically what it means is that we can find Laplace transforms for functions that have discontinuities in them, which we couldn't do in our other methods we had before. So that's why Laplace transform is so important. It will also exist if the function we're taking the Laplace transform is piecewise continuous and satisfies this condition that the absolute value of the function is always less than or equal to some constant m, e to the ct, where s is always greater than c, and m is basically a constant. And in most of the cases we're doing, that is true. It is going to be less than an exponential function. So, and what that means is it has an exponential order, which means that these functions will always have values that are less than or equal to an exponential function. So, now, I just want to review what the learning objectives are for today. So hopefully, at the end of this, Students should have a much better understanding of the definition of a Laplace transform. They should be able to find a Laplace transform using the definition. They should be able to find a Laplace transform using the table of Laplace transforms. They should also be able to find an inverse Laplace transform using the table of Laplace transforms. And know the definition of the unit step function and the Laplace transform of the unit step function. All right, so that's it for today. I'll see you in class.